Okay, so now let's go for the trigonometric equivalences here. Okay, so I'm going to use this plot here. Okay, so I'm going to use this plot to show that this is true. The absolute value of the sine of x is smaller or equal than the absolute value of x, which is smaller or equal than the tangent of x. Okay, so how do we know this is true? Well, the sine, and this is true where, between minus pi over 2 and pi over 2, right? Well, this is true for the first inequality, the sine of x. You can see this is smaller than this. It's kind of obvious from the picture, right? Or you can think about it in terms of areas, right? So the area of this triangle is, let's see. Well, actually, this is going to be smaller, right? Yes, it doesn't matter. So the sine of x and this curved x is obviously greater than this. Now, this x and the tangent is not so easy to see that this is smaller than this, but you can see this with the areas, right? So the area of the sector, this is x, this is a circular sector, and the area of this is 1/2 of the angle, and the angle here is the absolute value of x. But so this is area 1, and the area of this, this is 1, and this is the tangent of x. So the area of this triangle is 1/2 times the height, okay, the absolute value, okay. And we know that it's obvious that a sub 1 is smaller than a sub 2, right? So that means that 1/2 of the absolute value of x is smaller than 1/2 of the tangent of x. So we cancel each other out, and then we have this inequality, which is what we wanted, okay? And the smaller or equal is because when you go to pi over half, these things are, or 0, these things are similar or the same actually. Okay. Okay, so we start from this inequalities, okay, that we prove using geometric arguments. Okay. Now we can divide this thing by the left one by the absolute value of x. Then we have the sine of x divided by the absolute value of x is smaller than 1, smaller or equal than 1, right? Now I'm going to draw the sine of x between minus pi over 2 and pi over 2. This is pi over 2, and this is minus pi over 2, okay? So this, you can see that the sine, okay, the sine of sine of x is equal to the sine of x, right? When x is positive, the sine is positive. When x is negative, the sine is negative, right? So we can rewrite it like this: sine of x over x is greater than 0, okay? Because when both of them are negative, the quotient is positive. If x is between this minus pi over 2 and pi over 2, right? So then we can combine both inequalities and say 0 is smaller equal than sine over x smaller than 1, right? Okay, so let me write it like this, okay? So now, let's say from this inequality we have absolute value of x is smaller than the tangent, but the tangent is just the absolute value of the sine divided by the cosine, right? But we can rearrange this and say that the cosine of x is smaller or equal than the sine of x divided by the absolute value of x, right? But this is smaller than 1, so now we know that the cosine is smaller than 1. which kind of we knew because that's the bound, the upper bound for the cosine. But between minus pi over 2 and pi over 2, actually the cosine, there's something like this. This is pi over 2 and minus pi over 2. This is cosine of x. So this, we can get rid of the absolute value and say that the cosine is smaller or equal than 1, right? So then we have this bond, and we knew that this is smaller than this, so we have the cosine of x smaller or equal than the sine of x over x, which is smaller or equal than 1. Okay? So let's see. So now we have again epsilon sub n, a sequence that converges to 0. Then we have the sine of epsilon sub n is smaller or equal than epsilon sub n. Okay, applying here. And then we can this inequality implies that the sine is between these two numbers, right? Okay, if the sine of epsilon sub n is positive, then this is between smaller than this. If it's negative, it's greater than it, right? The absolute value is greater, closer to 0. Well, if now we take limits in both sides, we have the limit of this is 0, the limit of this is 0. So applying the sandwich theorem, the limit of the sine of epsilon sub n is 0, which is kind of something we knew, because the sine is this function that when it gets, its argument gets closer to 0, it's also getting closer to 0, right? But bear with me. So we have the limit of the sine is 0. Now the cosine of epsilon sub n is the square root of 1 minus the sine squared of epsilon sub n, right? Now the limit of this is 0, so the limit of the cosine is 1, right? Okay. Well, if we use this fact and go here, okay, with this we are going to rewrite, instead of x, we're going to rewrite epsilon sub n. We have epsilon sub n, epsilon sub n, epsilon sub n, right? There's this. If we take limits here, so this is the limit here, the limit, and the limit here is 1. This limit is 1. So again, using the sandwich theorem, we have that the sine of n of epsilon sub n divided by epsilon sub n, the limit of this is 1, using the sandwich theorem, which is one of the equivalences that we wanted to prove, right? So in other words, we have that the sine of epsilon sub n is equivalent to epsilon sub n, right? So this is what we want. Now finally, the limit when n goes to infinity of the tangent of epsilon sub n divided by epsilon sub n is just the limit when n goes to infinity of, and then we have the sine of epsilon sub n divided by epsilon sub n times 1 over the cosine of epsilon sub n, right? Because the tangent is sine over cosine. Now the limit of this is 1, we just proved it, and the limit of this is 1. So the limit of the tangent over the epsilon sub n is 1, so this is also equivalent to this.